the orbital element from the radar measurement observations. From radar observations, we are providing. Sorry, last time I forgot the other one. We also need the time varying information, which means speed of the radial distance, speed of the elevation angle, speed of the azimuth angles. So we are given those things, and basically we want to find is the R and V. Once we have R and V, in particular, that one is expressed in our IJK system. IJK is the geocentric coordinate system. Okay. So once we have the R and V, then basically in our your homework this time, say using the element EL or RB, using that kind of the functions, we can calculate all these 6 orbital elements. Okay, or this one is our this time is our homework, right? So that is the thinking process, and so basically right now we already done is we are given R and V, we know how to determine the orbital elements, and now we further down go to the application. We are given the observation here. Basically here the radars, the kind of those information are most of the time is given in the PQW. Inside in SEZ. SEZ system is we call the top centric. Okay, so basically from here to here we have to do a little bit the coordinate transformations and then doing something here. Okay. So to do this one, again, today our topic in this section is we are given this and we're going to find this one. And last time we have done is this, based upon the rows and those kind of information, we are able to calculate the expression in SEZ. Okay, we are able to determine the displacement and velocity which expressed in SEZ coordinate systems. So now we're going to start from here. And so here, our solution, here I'm going to list the procedures here first, and then we will look at one example second. So here the step 1 is we go to preparations. And preparation is the coordinate transfer, the transformations between IJK to SEZ, and that one we have done before. Let me recite the formulas first. So here we have x, y, z, and that is a coordinate in IJK coordinate systems, and then we can convert into the x, y, z into SEZ. That is the coordinate in SEZ system. Okay. We have seen this before, and that basically is a D matrix. And D matrix is in our textbook. So maybe let me rewrite again. So basically, this one is x, y, z, and coordinate system in SEZ, and that one will be equal to sine L0 minus cosine 1, 0, 0, cosine L0 sine 1. And here, what is L, what is theta? And let me give the definition here. So this is IJK. So for example, here, this is our radar site. So from these definitions, and we define this is theta here, measure is theta. And this is L. So theta basically here is an angle that is measured from the I-axis, okay? And this I-axis basically here, if you know, remember from the very beginning, this one basically is pointing to, I think the Aries, installation of Aries. Basically that is very far away, and that basically, in terms of the humans, couple hundred years of the lifespan, this direction, in terms of our Earth's viewpoint, pretty much fixed in space. So that means this one pointing to this one can be pretty much, we can see as a constant direction. It won't change over time in terms of our life. Although in the long, say, couple million years of the span, this one do change. But in terms of short of time, this one constant, okay? So here, the theta is measured from here. And what is L? L simply is the latitude of this. So compared to our radar's observations, basically here the elevation is, simply this one is our elevation, right? So in terms of the notation, this one is our elevations, if I'm right. Yes. Okay. And so now we keep this in mind, and theta will be depends on, say, right now, for example, you know, right now it's about 10:45 a.m. Before we go to details about how to determine the theta, and let me give you kind of side chatting. We just simply chatting how to measure the time. So right now today is 10:45 a.m. In October 16, 2017. Okay, and what this means? This means is here. This is the Earth. This is the equatorial plane. Say this is the North Pole, and this is the longitude of passing through the Fairbanks here. And here is the longitude that passing through, they call the Greenwich, and which is the people take it as a standard as the time measurement. So we know right now our time is 9 hours 4 behind the. Right now we're still not in the daytime savings. No, we're still in daytime savings. So right now we are 9 hours 4 behind. So basically at Greenwich local time they is 19. So that basically is the 7:45 p.m. They already done, almost finished Monday of today. Okay, so that's the Greenwich. And so here that is the K system and whatever the J. So here, for example, if this is the I system, so Greenwich basically here is the to this moment, Greenwich, we can measure the angle from Greenwich from the position of this angle to I. For example, let me say, I just after pick it up. Okay, so for example, here say it's 30 degrees. Right now in 7:47, sorry, I'm kind of like to chat. Right now in 7:47 p.m. at the Greenwich, we should able to, using whatever the almanac or whatever the book, we can determine what is the angle between the Greenwich longitude to the angle I here. Once we determine this one, then we always know this one angle between, this is the longitude between the Fairbanks and the Greenwich. That one is always fixed. And we know the Fairbanks has the longitude is how much? Minus 147 degrees, which means 147 to the west. Okay, so this angle is always fixed. So if we can know the Greenwich time at any moment compared to the I-axis, then we can always know anywhere in the world there's theta. So basically theta is measured in this way. Okay? Depends on which time and where you want to do something, then you have to determine theta. And later we will have one specific sections and using certain examples to demonstrate and how to determine theta. And actually, in our follow-up homework, and we will have one or two questions and ask you to exercise the theta. Okay. So in this way, we have this formula in mind, and quickly, as long as we know the radar side, we have a latitude, and we will learn how to exercise determine theta. So in this way, in these questions, in this equation, basically, if we have one coordinate on either coordinate system, we can determine the other one. So keep that in mind. And again, here we have the information, and so let me move on to here. Okay, so that is the step one. Step two. We try to begin to do something here. So here, let me draw the coordinate systems again. I, J, K, and basically this is the equatorial plane, the QUADORIAL plane. So this is the IJ plane. IJ plane is the equatorial plane. Okay. So here, for example, our radar is here. So this is the longitude. So again, we're going to exercise how to determine theta, don't worry. And this one, in dash, let me call this is the R vector. The R vector simply is measured from the center of the Earth to where the radar is. Okay, and basically here is the local coordinate systems. So this is our R. SEZ. So this is our Z directions, and this tangent to there. This is our S directions, and east. That is our east direction. So here is definition of the local SEZ coordinate systems. Okay. So here we have all the information. So from here, say for example, on top of our head, and our head here, say here is a satellite. I'm showing right now is in three-dimensional. Okay, so the satellite is here, and our measurement is this. We measure from from radar is this one. Okay, the measurement of the radar, of the satellites from radar, basically that is our sigma, right? Rho. And also this one, basically from radar measurement here, we have other informations. Rho EL and AZ, and rho dot EL dot and AZ dot. So those are the given informations with respect to the radar there. Okay. And one of the orbital elements, what we want to determine, if you remember in our equation here, this is our orbit and this is the occupied focus, which means it's the center of the Earth, and that is defined as R, right? In terms of these terminologies, which is R? R is this one. From the occupied focus, which is the origin of this one, measured to here. So this is R. Are we okay? We measure from the center of the Earth to the location of the satellite, that is R. So easily, so the first question is in step 2. With those kind of graphics in mind, what is R? We're looking at the vectors. R simply is equal to, look at the vector simply equal to rho plus R, right? We look at these two vectors. Okay, so now we have these vectors, and vectors right now depends on which coordinate system you're going to measure it. So now I'm going to impose from SEZ, from radar here, from radar, what right now I'm going to impose is the information given from the radar observation. In radar observation, we know that we measure the sigma is based on the local hypercentric coordinate system. So this data is available in SEZ coordinate system. That's a given, right? And if you remember last week, we have done certain calculation, rho SEZ and then rho dot SEZ. So we have done the two examples before, right? Okay. So here that is the given, the handy information from radar observations. Okay. So that one, if we stick with whatever we are given, so initially we try to express our information in SEZ. Then the next step, we apply that transformation to convert from SEZ to IJK. Okay, so now compared to this one, then we can see, so basically this one is, let me keep right, and this is SEZ. And what is R? The R is the, simply is this vector. This vector is measured in SEZ coordinate system. Basically R can be expressed as 0, 0, and R. In SEZ. Okay, in SEZ system, the first coordinate is pointing to S direction, the second coordinate in Z direction, the third coordinate is in Z direction, and Z direction which has the R here, right here. So here in this one, simply we express into that. Okay, so that is the calculation procedures. Once we have this one, then simply we plug in using that information. So therefore, whatever the coordinate systems we're going to measure in IJK, using that information simply is, this one is our XYZ, okay, in SEZ. So that is XYZ in SEZ coordinate systems. And that one we simply take the inverse. So this is our D matrix. Okay, so that is our D matrix. D matrix multiply with the IJK information given to SEZ. Inverse in SEZ, simply we take the D inverse here. And D inverse can be easily calculated, for example, in MATLAB. From here, I think from this time, the homework, you see gradually a lot of the more kind of computational rigors. And you will find if you have a MATLAB code, that'll be easy. And even for this one, so here I give you a hint for coming tests, test 2 and test 3, either they have certain, I will reserve the SoCal and for you to say, to do some calculation in front of the computers, okay? And get ready your functions, say either O or B, get that one ready. Once you have something down here, then you can use it for later on. We're going to use quite a bit those kind of functions. So now we have this one. So we done R. So now the step 3. We're going to determine V, I, J, K. To determine V, I, J, K, can I use? Okay, so let me get rid of this. Let me let me redraw these triangle relations here. So this is the IJK. That is basically is an IERTIL coordinate system. Okay, because I said the I-axis is basically pointing to a fixed place in universe. So I would say this is an inertial coordinate system. But you may argue this is not so accurate, but here we just take it, okay? So from here, say this is the, say point A here. So this is our satellite. And so let me say that is a point A, point B. And this is our SEZ coordinate systems. So SEZ, whatever which one, the SEZ coordinate systems. SEZ coordinate system is a moving coordinate systems. Okay, so from here we have done is, let me use the same color. So from here we measured is rho. And from here we measured is R. And okay, so I redraw these informations here. And let me call the coordinate here is point A. The point A is the origin of the moving frame. If you can recall the dynamics you learned before, the velocity at point B, and this one involves a moving frame and involve the measurement of something from the moving frame relative to the fixed frame. So if you can recall that kind of dynamics, and let me rewrite the equation here. So that basically that is equal to VA plus this one, basically these portions will be velocity of B relative to A. That's the concept. And regarding the moving frame, they have translation, they have rotation. Basically, this term can be rewrite into omega multiply with R B over A and plus V relative. Okay, let me explain this one by one here. That is the fundamental equations. Omega is the rotation of okay, so with this fundamental equation, let me plug into our equation here. So VB basically is what we're going to measure, the velocity, the satellite side V. Okay, so that is a satellite. And that is equal to V. And A right now is basically our radar site. And so that is V and at the radar site. And omega is the rotation of the moving frame, which means it's the rotation on the radar side. What is that? That simply is what things drive the radar side to rotate. Radar fixed on the surface of the Earth. So basically omega represent here is the rotation of the Earth. Got it? Okay? And then multiply with RP relative to A. So that is the distance measured from satellite respect to the radar site. Basically that is our rho. Got it? And this is a relative velocity. That is a velocity being seen from a person in the moving frame. So we are all in the moving frame. And we see from the radar's observation, we see the velocity. So that basically is this one. Okay? And furthermore, what is the velocity of the radar site? And here we are on the surface. Actually, we are being driven. We're kind of stuck on the surface because of the gravity. But in the meantime, the Earth is rotating. Not so fast, but really is very fast. We are not kind of spin off. It's because of the gravity, right? Otherwise, we will experience it's kind of the things, right? So basically, this radar site, and if you like, that one basically is this is a sphere, and this is the radius, and that is the Sabinian omega. So this one, basically, radar site is here that have the tangential velocity. Got it? Okay, so this one basically is omega multiplied with r. So therefore, here we can rewrite everything is omega and r plus rho and plus rho dot. Okay, r plus rho, basically I can rewrite the omega times r plus rho, basically is our capital R here. So velocity of the satellite, we can using these equations. That is simple enough. Okay, so box would be used for information, and we can start with any question to here. Everything in the process without box, that is for explanation for us to understand. And don't worry, and those one just simply the calculation. This one will be more useful. Okay, and now we want to impose is this. We are asking again. This is our this orbit, and here is R, and here is our V, right? Mm-hmm. And this one basically is the element we wish that one can be expressed in IJK. And already we have done this one for this one. So now we're going to for this one. So here we're going to impose is hopefully we can have this one expressed in IJK, right? So now in this way, if you want to describe this equation, well, this equation is a vector equation. The vector, we come to the very fundamental question here. So if this is a vector here, and let me call D. This vector right now I draw is basically pointing to there, and this vector always points to there. Doesn't care about which coordinate system we use to describe this one. For example, I can use the XY coordinate system to describe. In this way, the V should be equal to, under this case, V will be equal to, for example, here, say, 2, 1 vectors, okay? The same vectors, if I say using this coordinate system, say x prime, y prime, so in this way, this vector will be equal to, they say that is square 5 and 0. So the vector is always there, and doesn't matter which coordinate system we describe, the vector will always be there. The same reason here, if we have this vector, if I wish to describe this vector in any coordinate system, we can always do it. So here I simply assign, I want to express this one in ijk. So here I want to express this one in ijk. So that means individually, I wish the component can be in ijk. So that means omega will be in, once you determine omega, that should be express omega's the rotation of the Earth that in terms of ijk. So that means you can expect that omega only have k coordinate, right? You got it? And this one expressed in ijk, and what is our ijk? We have done this already. Here. Okay, so, and then what is this one? Rho dot ijk. So right now we look at these equations. This term is no, because this is the Earth, so this is the North Pole. We'll look at from the top of the North Pole, and the South Pole is on the other side. So from here, the omega simply is 0, 0 omega of ijk, right? So given this information. So that one, this is given. And our ijk, we've been calculated already here. So leaving, what is this one? Again, we utilize this equation here. So I would say put one more mark. So where the rho ijk dot can be equal to, again, from radar's calculation, from radar's observation, we already know, or we can calculate as easy. So that is from, this term is from radar observations, right? Okay, this one, basically this one is equal to rho s, rho dot e, and rho dot z. And the three terms, we have one exercise, very trivial exercise last time. So, and then what is this one? Look at this one. So that one basically is the inverse. All the information we want to calculate in ijk basically is the inverse multiplied with whatever available in SEZ. Because combining the two together, we will have the R&B. And we can look at one example to probably start a new section.